In this presentation, we'll talk about thermal expansion, which occurs due to an object changing temperature. So when the temperature of an object rises, basically what happens is that we know that the molecules that make up that substance are moving faster, so they're sort of jiggling faster and faster, and they're moving further apart, at least when we're talking about solids. But it's also true when we're talking about liquids and gases as well. And so what happens is because that temperature has increased and those molecules are moving faster, jiggling, they're spreading apart. And so most substances expand when they are heated, when their temperature rises, and contract when they are cooled to a lower temperature. There are some exceptions to this rule in terms of certain temperature ranges, and we'll talk about that specifically. So I always like to show this little picture here because I sometimes have a difficult time getting the lids off of containers that haven't been opened yet. And so if you run it under hot water and you heat that rim up of the container, the metal actually expands a little bit, and it makes it a little easier to take it off of that jar, which is a glass jar here. Other things that happen, and we're going to see some pictures, railroad tracks that are laid in the winter sometimes can expand and buckle in the hot summer, and I actually have some pictures of that. But in general, when you change the temperature of an object, if you cause the temperature to rise, the object will expand, and if you drop the temperature, it will contract. So here are some other pictures that are important. So here's a picture of a railroad track that obviously has had some issues because of when the track was laid. They did not allow for the expansion of that track as the temperature changed, and it caused the track to buckle. Other examples would be when we're constructing bridges. I'm sure everyone has seen this if they're driving or walking. A lot of times across the bridge there'll be this, looks almost like a zipper, right? And there's some gaps here, and that allows for the expansion and contraction of the bridge, which stops anything like this buckling from occurring. So it turns out that when we look at objects that expand when their temperature rises, that it does depend on what the substance is made of. So different substances expand at different rates. So this is a picture of something called a bimetallic strip, which is made of brass and iron. So there's a picture right here of it. And so what happens is that the temperature is increased, and there's a greater expansion that occurs for the brass strip compared to the iron strip. So a bimetallic strip, here's the bimetallic strip at room temperature, and it's basically made of these two different metals that are put together. And so if you heat them up, so here's a picture of it being heated up, the brass expands more than the iron, and so it gets this curve to it since they have to be stuck together. And the outside of this curve is a little bit longer, obviously, than the inside of this curve. So brass expands more when it is heated versus the iron. And then it also contracts more when cooled. So if it expands more when it's heated, it contracts more when it's cooled. So if you put ice on top of this, the brass would contract more, so that's the smaller length versus the iron. And so these bimetallic strips are often used as shutoffs in different types of thermal devices like heaters, oven thermometers, refrigerators, and toasters. What you can do is you can have these bimetallic strips, and if it gets too hot, it will like disconnect from the circuit, and then it'll automatically turn everything off. There's a lot of videos for demonstrations of this on YouTube, so you could certainly look up bimetallic strip and see some videos for that. And then this is just another picture that represents the same thing. If I was preparing a lecture for this in class, I would actually pull out a Bunsen burner and a bimetallic strip, and we could show this. In general, the change in the length, how much this thing expands or contracts, the change in length depends on the original length of the substance, so how long was it to start with. It also depends on how much you change the temperature, so delta T. If you don't change the temperature of the substance at all, it's not going to expand or contract. And it depends on the type of material that you have. So in that previous example, the brass expanded and contracted more than the iron. So the type of material is going to affect how much the length changes. And the type of material in the expression that tells us linear expansion is this alpha right here. And it's called the coefficient of linear expansion. And so it will, there will be different coefficients of linear expansion for different materials. So here is a little animation where I have fine ceramics, so it's alumina here, and then I have stainless steel down at the bottom, and I've got these flames, so they're both being heated the same, but the fine ceramic here is only expanding a little bit, so the delta L for the ceramic is pretty small, but the delta L down here for the metal is much larger. So that means that they started off at exactly the same length, but the steel expanded more, changed the length more, so the coefficient of expansion for the steel is greater than the coefficient of expansion for the alumina. Oops. Right here, the fine ceramics. I just put AL for that one. So it turns out that there is, and I'm not going to spend a lot of time on this, but there is an exception to the rule in terms of expansion, and that is water. So in general, objects tend to expand when they're heated, when their temperature rises, and contract when they're cool and when their temperature drops. The exception to that rule is water. So water behaves weird between 0 degrees and 4 degrees Celsius. So what happens is that everything behaves normal. Water is normal for all temperature ranges until you reach 4 degrees Celsius. So what happens is that when water, so let's just sort of try to talk through this kind of quickly. So suppose you had a pond and you were to go swimming in a pond or a lake, and so it's warm outside, right? So that you put your foot in the lake or the pond, and it feels really nice and warm at the top, right? So you're like, I'm going to jump in, and then you jump in, and at the bottom, the water is actually pretty cold. And so what happens is that on a warm day, the water at the top is very warm. The water at the bottom is cooler. So if we think about just in general, as water is cooled, in general terms, as water is cooled, that means that it contracts, right? So its volume decreases. And as its volume decreases, according to density, density increases. So water cools down. Let's say it's really warm outside, really warm at the top, but then it cools down, really cool at night. So the top layer of that water cools down, and as it cools down, it contracts. It becomes more dense than the warmer water below, and because it's more dense, it sinks. So the cooler water sinks to the bottom, and the warmer water rises to the top because it's less dense. And that occurs, that's normal for the normal temperature ranges. And then you reach 4 degrees Celsius. So what happens is in the fall, when the water temperatures are rising or dropping, and it's starting to get to the time when it's going to be winter and the ponds and lakes are going to freeze over. So then the temperature reaches 4 degrees Celsius. So water cools from 4 degrees Celsius to 3 degrees Celsius. And what happens is that instead of contracting, instead of doing what it should do, temperature is dropping, it should contract, it doesn't. Instead of contracting, it actually expands. So as the water expands, the volume increases, and that means that its density decreases. So what does that mean? That means that 4 degrees Celsius water is actually more dense than 3 degrees Celsius water. So the cooler water is going to stay on the top. So that's not normal, right? So in general, what should happen is the colder it is, the more compact it is, the more dense it is. But water behaves weird between 4 and 0 degrees Celsius. So as it cools in that 1 degree Celsius, the water actually expands, becomes less dense, and the 3 degree Celsius water will stay on the top instead of sinking to the bottom. And that process continues. So when the temperature outside gets to 2 degrees Celsius, the water drops from 3 to 2. And again, instead of contracting, that water expands. The 2 degrees Celsius water is less dense than 3 degrees Celsius. It stays on the top, and the process continues. So you get these regions, essentially. It wouldn't be exactly cutoffs like this, but 4 degrees Celsius water is at the bottom, and then you get these kind of layers until you get up to the top where it's 0 degrees Celsius. And as we know, water freezes at 0 degrees Celsius. So what happens is that ice forms on the top of the lake or the pond and not at the bottom. Because if water was behaving normally, then the temperature at the bottom would be 0, and then 1, and then 2, and then 3, and then 4, but it's behaving weird between 4 and 0 degrees Celsius. So this allows ice to form on the top of a lake or a pond rather than at the bottom. It allows water to not freeze down here, which allows aquatic life to actually survive during the winter. So from what I just mentioned, this is sort of a discussion of that. I'm not going to talk through it again, but I discussed it on that previous slide. Okay, so let's look at a couple of conceptual examples. So suppose that we have these various materials that are all at the same length, and they have the same initial temperature. But we want to increase their temperature by 50 degrees Celsius. So they start off at some temperature, and we're going to increase the temperature by 50 degrees Celsius. Which of these is going to expand the most? So we have their coefficients of expansion, and these are all times 10 to the minus 6 because coefficient of expansions are very small. The material that's going to expand the most is the one that has the largest coefficient of expansion. So when I compare all of these, lead has the largest coefficient of expansion. So it will expand the most. We can also ask the same question, except we're going to, which one is going to expand the least? So obviously the one that has the smallest coefficient of expansion will expand the least, which is copper in these cases. Same question, right? Except now we want to decrease the temperature by 50 degrees Celsius. Which of these is going to contract the most? So the coefficient of expansion actually tells us which one will expand the most and contract the most. So the object that expands the most also contracts the most, and so lead would actually contract the most of all of these because it has the largest coefficient of expansion. So we talked earlier about these bimetallic strips, which are basically just 2 strips of metal that are placed together, and they're like bound together. And so they're going to expand differently, and then whichever one expands more, because they are sort of tied together, is going to cause this to bend. And the arc would be, the outside of the arc would be whichever one expands the most. So here we have a question. A bimetallic strip is made from copper and aluminum. The copper is located on the top and the aluminum is on the bottom. The strip is heated. Which way will this strip bend? So I've given the coefficients of expansion. Copper's on the top. It's not going to expand as much as the aluminum, which has a larger coefficient of expansion. So this is going to expand more. So the curve should be upward, right? It should be curved like this because the aluminum has to have room to expand more than the copper. So it will expand upward. If I had these materials, which of the materials should I place together in order to get the greatest bend in the bimetallic strip? So if I want to have the greatest bend, I want to have the greatest difference in their coefficients of expansion, right? So I look at these, and the first one, I see lead is largest, and copper is smallest. So if there's a combination of lead and copper, that's going to produce the greatest bend, since that is the one that has the biggest difference in the coefficients of expansion. And so there we go, copper and lead. If I were going to put two of these substances together, it was just a harder question because I've got 17, 18, and 19, so we won't answer that question. But definitely the biggest bend would occur between the two that have the greatest difference in coefficients of expansion. The least bending would occur between the substances that have the closest coefficients of expansion. So finally, we can look at just a really quick example. We have a length of steel that's used in the construction of a baseball stadium. The length is 30 meters, and that's the initial length. And that's at 20 degrees Celsius. And so we want to know how much is it going to expand if the temperature reaches 30 degrees Celsius. So the change in temperature from 20 to 30 is 10 degrees. I also know the coefficient of expansion is this really small number here for steel. I can determine what the change in length of the steel piece is. It's just the initial length times the coefficient of expansion times the change in temperature. So 30 meters, I actually switched these around. This is the coefficient of expansion times the change in temperature. The change in length would be 0.0036 meters. Sorry, something happened there and it was automatically putting everything on. So the change in length would only be 0.036 meters.